proof that the Goldbachs conjecture is true.
Let x be an even number.
Every odd number under half of x pairs with an odd number above half of x to sum to x. An odd number never pairs with an even number, so we can eliminate all non-prime pairs using the sieve. So by doubling the primary sieve to remove all multiples of primes less than the square root of x and the odd number which they pair with and sum to make x. The only odd numbers remaining must be primes and in pairs of locations which sum to x.
What this double sieve does is establish a minimum number of prime pairs for each value of x. This minimum can be exceeded, for example, where x has odd prime factors. Where x has odd prime factors, the composites made from the factors pair and sum to x, which leaves more locations for primes, therefore more prime pairs. When we run the sieve at 5 squared plus 1, there is a minimum 2.6 primes left, therefore a minimum 1 pair. At 7 squared plus 1, the minimum after the double sieve is 3.571 primes, so 1 prime pair. Remember, that's just the absolute minimum. In reality, we have more because 5 is a prime factor of 50. At 13 squared plus 1, the minimum is 8.406 primes left, therefore a minimum 4 pairs. But again, 170 has 5 as a factor, so we expect more than the minimum, and we do. We get 9 pairs. So now the irreversible trend upwards is already clearly visible. And the mechanism which proves that an exception is impossible is because for any two consecutive values of x, which are p squared plus 1, both of these values of x will be in a range of integers where the density of primes to integers is the same. Therefore, the ratio of primes to x will be the same for both numbers before the highest prime below the square root of x. For the higher valued x is deducted in the sieve. Then both values of x will have the same ratio of primes to x. So because the second x is higher, it must have more primes left over after the double sieve than the lower x. Then, when we take the final deduction for the final 2 divided by prime for the highest prime below the square root of x, it is a smaller fraction than the previous final deduction for the previous p squared plus 1. So the number of primes for each new prime squared plus 1 can only increase. I give 2 examples here if anybody wants to stop the video, and I'll put it in text in the video description for anyone who's visually impaired who wants it read out via text to voice. So because this mathematical mechanism forces the numbers to go higher towards infinity, and because we would need less than 2 primes left after the sieve for the conjecture not to be true, it means Goldbachs' conjecture is definitely true.